Okay, so now I shall announce the speak. The speaker is Christian Grothoff. He's the maintainer of GNU Net, and he's being assisted by Florian Dold, who's sitting there and is a student at the TU Munich and is a student assistant for the same project. And it's about GNU NS, alternative to DNS. So have fun.
Thank you. Now, I want to begin by saying this is not just the two of us working on it. In particular, I have some co-authors, Matthias Wachs and Martin Schanzenbach. And then there are a bunch of people who have contributed code, ideas. I'm not going to read the names to you here, but it's a long list. And I might want to mention that this was funded by the DFG, as some people really are afraid of government funding, but they didn't do any involvement. We didn't get any calls. OK. So where are we? Well, we are in a world with environmental disasters, and the resulting unrest among the civil population is being countered by authoritarian institutions with surveillance to suppress dissent. And well, it's a difficult situation. So in this situation, we want to protect our privacy, our civil liberties. And so our adversary model, as we now know, has to be a rather strong one. So we have to assume the adversary can have any role, can have multiple identities, has lots of computational power, has legal power, national security letters, subpoenas, give me your private key, please. Now, we still want to assume that he can't break or prevent the use of cryptography because, well, if he can do that, we're pretty much screwed. We hope he doesn't compromise every end-user system out there. Again, that's a bit of a strong assumption, but again, if he does that, I can't help. And we assume he doesn't want to prevent network communication overall. Again, the economic cost of doing so, the economic cost of controlling all communication is presumably too high even for that kind of adversary. So if we have that kind of adversary and we say, OK, we want to secure our communication by using encryption, one fundamental thing all of our systems rely on is the public key infrastructure. And the public key infrastructure is broken under this adversary model that we have. And so when we look at the various systems that have been compromised recently, Skype, bought by Microsoft and now easily controlled. Lavabit, give me your keys. Thank you very much. Prism, I've sent stuff to a central server. Central server is easily taken over. DigiNotar, well, I've trusted some authority, and, well, the trust was somewhat misplaced. It doesn't matter if my encryption is the best encryption on the planet. If the PKI is broken, everything is lost, right? So we must decentralize. And we really need to look at this. Centralized infrastructure, as we have today, is easily controlled. IANA controls the number of resources. There's the root zone, the DNSSEC root certificate, X509CAs, major browser vendors. All of these live in one country, pretty much, or have a significant business presence in one country, and are therefore subject to the laws of that country. And we know that that country is not known for respecting users' privacy. So we need to decentralize. Now, when we try to build a decentralized PKI, one of the fundamental insights in this domain comes from Zuku. It's called Zuku's triangle. Some of you might have heard about it before. And what he said is, well, we want three things from a name system. We want it to be secure. We want the names to be global. We want the names to be memorable. Okay, global names means the meaning for a name is the same for everybody on the planet. If they ask for it, they get the same value, ideally. Memorable means I can pick names that I like. Alice, Bob, not here's some cryptographic 512-bit identifier, remember that, and type it incorrectly every time. And secure, well, secure is kind of a bit fuzzy. What does it all include? But we have to, again, think secure as with respect to the adversary model we have. If we have a trust anchor like the DNS root zone, like an X509 certificate authority, that's no longer secure. Right? And if you decide, well, secure is not that strong, the adversary, then, well, Zuku's triangle doesn't hold. But if you really look at this adversary model, you have to say, OK, we can't have all three. Let's look at some examples for those systems that have two of them. So with global and memorable names, we have hierarchical registration, the classical domain name system. I assume everybody is somewhat familiar with that. With cryptographic identifiers, we have global names that are perfectly secure. The public key is in the name. So we can then sign the records with that public key, and if the crypto is fine, it's all good. But, well, they're not memorable. I've not yet seen a crypto system that has a public key that I can memorize easily. And memorable and secure, well, there's pet name systems. So the easiest example of this is your etc host file. In there, you can put a memorable name and a number. And as long as your computer isn't compromised, you don't even need crypto. You will get that name mapped to a number, but it's not useful for anybody else. It's a least global system. It's only for you. Right? Now, there are designs to try to improve this. If you look at DNSSEC, where we add certificates to DNS, it's trying to make DNS a bit more secure. Right? We don't quite get all the way secure, given our adversary model. There's mnemonic URLs, which the idea is, OK, let's make a phrase that makes it easy to remember this 512-bit string. It's a suggestion by the tour guys. It's a serious suggestion. And the problem is, for me, when I define memorable, I say low entropy. And of course, I don't get away with the entropy. I need to keep the information there. And yes, maybe this broken English sentence is a bit easier to remember than a 512-bit key. But again, we don't really get memorable, right? And then there's an approach called SATSI, which effectively says, OK, we have these pet name systems. How about I make my pet names available to you? So I put them into a public database. And then you can query my names, as long as you have a name for me. So we get kind of transitivity. You can use my names. They're no longer just for me, but they're not truly global. Right? Everybody has his own perspective. And this is kind of the foundation for the GNU Name System. Now, some people here might say, OK, what about Namecoin? There was a nice article by Aaron Schwartz that said squaring Zuku's triangle. And I said, Namecoin, right? Bitcoin allows us to fix that. OK, well, the names in Namecoin, I give them, they're memorable. Check that. Are they global? Yeah, check that. Are they secure? Well, they have a different adversary model. Right? To start with, availability of names. So availability is a security goal. Well, they limit the registration rate. I can't just register 1 billion domains today. There's not enough Namecoin out there to do that. And the second problem is the adversary must not have 51% of the compute power. So aside from inefficiency and so on, the assumption that is made is the adversary is not very strong computationally. I'm again not sure that that is necessarily true, given what we know about the buildings in Utah and in the rest of the world. Or maybe the NSA has a nice botnet too. Huh. They do, right? OK. So let's talk about the GNU Name System. So we have a decentralized name system with secure memorable names. So you start by editing your own zone. And you can make those names available to others by signing them and publishing them online. As I said, you get this delegation property from SATSI that others, when they have learned your zone's key, can look up names in your zone. We also support global unique secure identifiers. So the .onion style, where you have your public key as an identifier, you can use that too. Nobody said that you cannot have two different name systems combined. So we can take this side of the triangle, that side of the triangle, that side of the triangle, and mix and match. We just don't get one name that has all of them at the same time. We have in addition to this query and response privacy. So when you do a query in the system, in DNS, everybody at the NSA can see what name you're looking up and what the answer was that you got back. In our case, we want to make sure that we make this as private as possible, so it's not trivial for anybody to figure out what you did. And as a result, we get an alternative public key infrastructure. And I say it this way because we can use this to replace the Web of Trust. We can use this to replace X509 CAs. We can use this to replace DNSSEC. Doesn't mean any of these are the best things to replace. We first want to focus on peer-to-peer networks, social applications, identity management in this kind of scenarios, because there we don't have to worry about interoperability so much. But in principle, for all of these things, we have a new public key infrastructure. And we can be interoperable with DNS by making our record types be the same as DNS record types, and then we have some more. OK, let me first start with what does this really look like from the user's perspective? And this is not the user quite that we might want in the end for usability purpose, but suppose you're currently a DNS administrator and you're administering a zone. What does it mean for you to switch to GNS? Well, we have a zone editor, which is here graphically. All of the screenshots are real, by the way. Somebody questioned that before. No, they are all real. You have your normal labels, the record types, the value you want to map to, and some expiration time. So you pretty much get the same experience as you would get from DNS in terms of managing a zone. Right, nothing really changes there. So suppose we have Bob here. He has his web server, and he puts into his local zone www is reachable at the IP address 5678. Good. Next thing he's going to do, he's going to make himself a little business card, like the ones that our Holland Foundation is willing to print for you guys at this event. And on this business card, he's going to put his public key. Okay? And with that, he can introduce himself to his friends. So he goes to Alice. Alice learns Bob's public key and puts into her zone, under the label Bob, Bob's public key. And here's the new record type we have for the public key of another entity. Once she's done that, she can reach Bob's web server under www.bob.gnu. Notice .gnu stands for me, because that's myself, my zone, the one that I control, that I have all freedoms over. Right? The freedom to give it to others, the freedom to change any name I want. Yeah. Now, how does this work? Remember, we have the following setup. Bob has his zone database. Alice has her zone database with an entry for Bob. And we have in the middle the peer-to-peer network with a distributed hash table. So distributed hash table, for those that don't know, just think hash table. Okay? Okay, so first thing what Bob does is he periodically stores the records from his database in the DHT. Just store them. Periodically, because, well, records in the distributed hash table tend to sometimes go away. Now, when Alice says, OK, who is www.bob.gnu, first thing her resolver does is, OK, GNU means it's my own zone. Who's Bob? Asks her database, who's Bob? The database comes back and says, Bob's public key is whatever, some public key. And she says, OK, dear DHT, who is www in that zone? And the DHT comes back and says, OK, here's your record. Now, that was easy, right? And if we have that, and we have this securely, we can put creative records in there. For example, here, I have an actual screenshot of Firefox where I put into my zone freedom.gnu, put in GNU's IP address and GNU's TLSA record, and my browser now has said, oh, I validated this against the GNU Name System certificate authority, because, well, that's what the proxy says the CA was when it created the respective validation certificates on the fly. Great. Now, where's the security problem here? Well, we have this little thing, DHT, in the middle, right? The magic box. Right? So what we have here is, well, what it looks like is the DHT can see what's being put in, what I get out, and, well, they could do whatever they want to the contents, right? So here's where we need crypto. OK, here comes the crypto. So we use elliptic curves, Dan's wonderful curve, because it's short in terms of public key size. So in elliptic curve cryptography, I'm just giving a brief refresher here. You have a generator, G, the point on the curve. The size of the elliptic curve group, n, it's a prime number. So these are publicly known values that everybody knows. They were set in stone once per curve forever. Then I have a private key, which I'm going to refer to as small x. So that's the secret for my zone that I have to protect, obviously. Then I have a public key. That's the point on the curve, which is calculated by, well, doing x times g. Remember, x is a number, so x times g just means adding the point g x times to itself. That gives me another point p, if I know what curve point addition is. And all we really need to know is elliptic curve cryptography says, given p, I cannot get back to x. Right? I can't really prove that fundamentally. We just don't know anybody who knows how to do that. Right? It's like factoring primes or large products. OK. Now, what we also have is we have a label for the record in the zone. So that's the www, for example, right? Or the name Bob. Right, so that's, again, we're going to map that label to a number mod n. Then we have a set of records for the label L in zone P. So that's the plain text records, like the IP address for the web server is 12345. And then we have the query hash, which is what we're going to use to store the information under in the DHT. So I didn't quite say how I get this, but we have to have some hash code for the hash table. And in the hash table, we're not going to store the records in plain text. We're going to store them in encrypted form. So I'm going to call that the BPL, the block for zone P and the label L with all of the records under that label. OK? That's just basic terms. So given this, how do I publish? First thing I do is I calculate the hash of the label and the public key. I do some hash function, and I get a small h. And then that's just a number. Again, can treat a hash as a number. I'm going to multiply hash with the secret x to get a derived secret d. So d is now another private key on the same curve. Right? It's just a number. That's why it's also mod n. Now, using that d, I can sign using ECDSA. What I'm going to sign is I'm going to encrypt the records with a key derived, again, from the label and the public key. So that's a hash key derivation function here. And I'm going to add d times g at the end. That's the public key corresponding to d. so that people can verify that signature using that information. I'm going to store all of this under the hash of d times g. That's my query. What does this mean for an attacker? Well, given the information stored in the hash table, d times g, I can't get back to x, I can't get back to h. That's the standard ECC assumption that we have. Given that the records were encrypted with the label and the public key of the zone, unless I know exactly what label and what public key it was, I can't decrypt. Now, if I know what the label and the public key was, well, then I could ask the same question, and then I have to be able to decrypt if it's a public record. So we can't fix that, right? But unless I can guess exactly the label and the public key, I will learn nothing. I will not be able to decrypt the records, but I can still verify that the signature is correct. I can say, oh yeah, that signature SD, right, signed with the private key D, matches with this public key. So intermediaries in the DHT can verify that the records are correct. They will not even cache invalid records, but they cannot decrypt what the contents were. They cannot tell which zone they belong to, none of that. Now, when I look for a label for the values, what I do is, again, I can calculate small h of L and P, hashing those. Now I can calculate h times P, right, which is the same as h times x times g, which is the same as h times d times g, which gives me the query. And then I can use this to obtain the encrypted block from the DHT, and I can decrypt again because I can do the HKDF myself also. So here I've got query privacy. And of course, integrity checking authenticity at the same time. Okay, one issue that we sometimes face is that people lose their keys. We might want to revoke them and say, okay, don't use this anymore. The basic idea of revocation is, of course, I create a revocation certificate in which I'm saying, oh, this private key is no longer valid. So I'm using my private key, sign a message and say, forget about this private key. Now, whenever a peer receives a valid revocation certificate, what we do is we flood it to all of the neighbors. Because a peer-to-peer flood is really hard to stop. Right? Even if you've got a couple of compromised guys, well, they'll just flood around them. Right? It's just islands in the ocean. All of the peers that receive a valid revocation certificate are going to store it forever. And whenever they encounter a certificate or a private key, they're going to check against the list, has this been revoked? Now, this is, of course, an expensive operation. Flooding the network, we must not be able to do this every 5 milliseconds. That will take down the network. And storing it forever, well, we don't want people to be able to store stuff forever on our machines. So here we're going to use an expensive proof of work using the scrypt hash function, effectively forcing you to do a calculation on your computer for a couple of days before you can cause this flood that will have to be stored forever. But once you've done that, it's pretty much impossible to stop the revocation. And then there's also no latency for checking has this private key be revoked. Now, there's a bit more revocation magic needed here. And specifically, there might be peers that are offline during the initial flood. So they might have missed that this thing was revoked. Or I might have a network that was partitioned. I might have had Egypt being cut off from the internet for a couple of months. And now these guys come back online, and they've missed a lot of revocations that might have been important to them. Well, if they really were cut off, I couldn't have gotten to them during that time. But now that we're reconnecting, I need to kind of get the sets back together. So we need to reconcile the revocation sets whenever peers connect to each other. So we need to compute the set union of those revocation sets. Now that sounds expensive, right? Not quite, Florian.
Hi, so let's do, does the microphone work? Yes. So let's do efficient set union. So just up front, this idea is not ours, but based on an idea by Epstein and others. And this was first presented in 2011, so this is kind of recent work. And we were the first one to provide public and free software implementation. So the basic setting here is that we have our two players, Bob and Alice, and they have two sets, A and B. And those sets are very large. They contain all the revocations of the system, but their symmetric difference is really low. And we want to exploit exactly that to reconcile them efficiently. So what do you want to do? Alice wants to know the set B minus A. That's the stuff she doesn't know. And Bob wants to know A minus B. Those are exactly the element he's missing. So let's talk about how we can do this efficiently. The first approach, which is a really bad solution, would be just to have Alice send her set to Bob. Then Bob can compute what elements Alice needs and sends it back. And then you do exactly the reverse thing. But that is really bad. It has a really bad communication cost because it grows with the size of the whole revocation set. What we want to do is we want to have an algorithm that can do the reconciliation in time proportional to the symmetric sets difference. So only the elements that we missed, for example, because we had a downtime, are actually counting into the runtime for our algorithm. So one first improvement that doesn't really work, we can just not send whole elements, but the hashes of elements, but that doesn't improve the runtime. That just makes each element smaller. So let's look at some more fancy protocol. So a very important basic building block for that most of you probably know from networking are Bloom filters. So a Bloom filter it's basically a data structure that has a fixed size that is some kind of summary for a set. So the basic operations for that, you can create one and then you specify a size for it. And the size of the Bloom filter and the memory necessary to represent it will never change. You can insert elements into the Bloom filter and then you can check whether an element was previously inserted in the Bloom filter. And this operation is not this is probabilistic. So you get an answer that either says the element is definitely not in the set, or you'll get an answer that the element probably is in the set. So let's look at how this works. So basically, a Bloom filter is just an array of buckets, and those are binary buckets, so they store either 0 or 1. And let's insert an element in this. This element 1 here gets sent to a hash function, and this hash function just gives us a number of buckets. So there's indices for these buckets. So for example, for element 1, we get buckets 2, 3, and 7. So let's insert our element into this. It's obvious we just set it to 1. Let's insert another element. This hashes to different values, and we just set those to 1. Now that we have inserted those two elements, we can check membership by just also hashing the element and checking if all the buckets that this element hashes into are set to 1. So if one of the buckets is 0, the element could not have been inserted into the set. But now here's a more problematic case. We have an element that's definitely not in this set. It's this element 4, but incidentally it hashes to buckets where previously some other element hashed into, and then we'll get a false positive. So Bloom filters are not enough to do set reconciliation. We need to do some extensions on them. The first extension are counting Bloom filters. So it's the same as a normal Bloom filter, but the bucket does not store binary values, but it stores a count. And by this, you can also remove elements from the set. Because if you only have binary count and then remove an element, you don't know if there was a previous element in exactly that bucket that has been inserted. So you need to have a real count and not just binary. The problem with that, but it's not really important, is that you can have false negatives if you remove an element from a Bloom filter that was not previously inserted. But that's also not sufficient for set reconciliation. For that, we need invertible Bloom filters. So here we also allow negative counts, and we do not only have the count field, but we also store an X or sum of element hashes in the buckets. We'll see an example soon. And they're called invertible Bloom filters because for them you can define extract operation that gives you the hash of an element that you previously inserted, which is really nice. And this does not always work because it's it's a data structure with a fixed size, and we can insert as many elements as we want into it. So the extract operation will return a result code that says either yes, we could extract the element and it had a negative count, we can extract the element and it had a positive count, we're done, so there's no more elements in the invertible Bloom filter, or it just failed, then we're out of luck. The next operation you can also define on those inverted Bloom filters is an operation for the symmetric difference. So you put two inverted Bloom filters into it, and you get another one that represents exactly Bloom filter where the symmetric difference of the two sets is stored in, but you tag from which sides the element comes from with either positive or a negative count. So let's look at an example for those inverted Bloom filters. Just this part here is from the usual Bloom filter, and here we have our additional bucket with the hashes. So now our hash function does not only give us a list of buckets, but also a hash value that we can insert here. So let's insert this element. Just the XOR with 0 results in the number itself. And if we have the count, let's insert another element. So here the differences are you actually count to 2, and here you just compute the XOR. So now that we have inserted all those elements, we want to extract them. And for that, we use so-called pure buckets. So pure buckets is a bucket where only one element is inserted. And if there's only one element, this field here stores the hash, which is exactly what we want. So we can extract the hash and reverse the operation for all of the other buckets. So this bucket here that currently has a count of 2 will get a count of 1, and then we can use the extract operation again to get the next element. But this, of course, will only work if we initially have a pure bucket. So the more elements we have in our Bloom filter, the less the chance that we can actually extract elements. So in a relatively full IBF, we will not be able to extract Bloom filters. So let's define the symmetric difference operations. This is really easy to compute. We just subtract the counts, obviously, and then we XOR the hashes. So let's see how we can use this for the set reconciliation protocol. So our two players put all their elements in an IBF and then exchange it and compute the symmetric difference. And now they can start extracting elements. Because there's only the symmetric difference in the Bloom filter, and we said that the symmetric difference is really small, it will be very likely that there's a pure bucket in the resulting difference IBF, and we can start to extract. And if that fails, we have just to repeat that with a larger IBF. So one thing that's missing here is that we have no idea how large the IBF should initially be. So for that, there's an additional step previously where we do a difference estimation. So we estimate the size of the symmetric difference for the sets. It turns out we can reuse IBFs for that. They're really suitable here because you can estimate the difference accurately for, especially when it is very small. So other approaches to that work much better when the difference is really large, but that's not our case here. And the basic ideas for the difference estimation is that you sample your set by looking at the hash, so for example, the number of leading zeros, and then you put it in this structure here. Those are all invertible Bloom filters, and here many elements are sampled, and the more we get to the outside, less elements are sampled. So now that we have created this data structure, of course, both peers have to create this data structure and then subtract the invertible Bloom filters element by element, and then we can try to decode them. So the first one will probably work, and let's say we get 3 elements out of that, 3 times the extraction succeeded, and we're done with it. Next one succeeds too, and we get more elements because we have sampled more elements into this structure. And let's say the next one fails. So we have no idea how many elements are in this one. But now we can do an estimation. because we have a relationship how many items we have sampled into this Bloom filter to this Bloom filter. So for example, we can say in one outer layer there will be just half of the elements. So let's look at this. Here we have counted 3 plus 7, so 10 elements. And then there are those Bloom filters that did not decode because they had a larger number of elements. But we can just estimate that because this one will contain twice as much as those combined, and this again will contain twice as much combined. So if you multiply it by 4, we have an estimate for the set difference, and then we can use our IBF.
Thank you. So as you can see, in a tiny problem like revocation, there's always a bigger problem. Now the nice thing is if you use the GNU framework for writing your own applications, you have this efficient set reconciliation as a nice API, and you don't have to care about the details, in case you want it. You're welcome. Now, back to the GNU Name System. Now that we know how to deal with revocation, there's also, as I mentioned, global cryptographic identifiers. That's what we call the ZKey TLD. So when you have the memorable ones, you add .gnu at the end. If you have a public key and you have typed it in, painful, I know, then you put .zkey at the end, you have a global name. Now this is just your entry point, right? Your entry zone. Before that global name, you can again put arbitrary labels that follow the normal delegation and are readable. So this kind of works a bit like .onion. Now, then we also have the problem that if you have these delegation chains, they might get a bit long at times. So it might be, alice.bob.carol.dave.gnu. It's now well defined, but not quite usable. Not to mention, every time we type this in, we have to kind of trust the zone of Dave, the zone of Carol, the zone of Bob to get to Alice. So, well, we can do better. And we have one more problem. Alice, who we have here, would really like to be called Krista. All right, just Bob calls her Alice, but that's a slander attack, right? So what we do is we add a new record type we call nick records. Let's say Krista specifies that her preferred nickname is Krista. Right? We add this to every record set automatically once it's configured. And so when Eve first uses that name for the first time, she learns that nickname and she puts it to her database an entry saying krista.short.gnu. The short version of this long thing is now krista.short.gnu. She learned this automatically. Now in the future, she just has this much shorter name for it that she got automatically. Now Krista has an important incentive here. She needs to pick a unique pseudonym. Right? If there are too many Kristas out there, this will not work because there can only be one krista.short.gnu. Doesn't have to be globally unique. Just within her social context, it has to be unique. Right? So, in short, we get a memorable short trust path for future use. You can consider this a form of tofu, trust on first use. Right? Once I've looked it up, I now have a short handle for it. OK. One other problem is we use this DHT. Now, in the DHT, you have latency. I might put a record in, and it takes some time for the record to be propagated, replicated in the DHT, be available, be fetched by users from the DHT. And sometimes when I have a DNS-like system, I want to change the mapping. Might be my server is going to be moved from the US to Europe on the 1st of January. And I really would not like to have the old records be valid at that point. And I need the users to get to the new records, but I don't want to be down for 3 days while things propagate in the DHT. Okay, maybe 3 days is a bit long for a DHT even, but ideally we have no downtime. So how do we do this? Well, you can put into your normal record set shadow records. A shadow record is effectively saying, this record is not valid as long as any other record under the same label with the same type is valid. So you say they set the expiration date for the old one to the 31st of December, right? Put in a shadow record that has a validity of 2014, and then the shadow record will not be considered as valid until the time where the other record expires. So it's a little trick to make this caching work nicely without having this problem that we need to, at this very particular time, get an update to everybody in the network. So it's just a flag in the network. OK, now practical concerns. Well, wanted to address a couple of them. So there's name registration, support for browsing, new record types, integration with application, state of the implementation. 5 minutes. OK. So registering a name in GNS, OK, we saw the first version. I give you my card, and you have it. Second possibility is we can, of course, still have a registrar. We are running the GNUnet fcfs registrar GNU.org. You can go there, first come, first serve. If you trust our registrar, It promises it will never remove your keys, right? And you can use it. And we actually ship that with the distribution as a public key under pin.gnu. So if you see somebody foo.pin.gnu, well, you're using our registrar. But you have very good trust agility here. You can choose to put another registrar, you can on your own. Either way, it doesn't matter. And many paths can lead to the same user or the same zone, right? So if one registrar is bad, we'll just use another one. Not quite so easy with .com these days. Yeah, so after this import, we can resolve Bob. Now, from DNS to GNS, well, in GNS, names are not globally unique, but we have these issues where we do web browsing like virtual hosting and SSL, where existing protocols assume that the HTTP host header contains the host name, and the web server really wants it to be the right one. And in the SSL certificate, it says, grotov.org, and it doesn't say grotov.gnu, and hence browsers will hate it. So one solution for this we deployed is the client-side SOX proxy, effectively a proxy that fakes everything up for the browser and makes it happy. Right? So you can put into GNS a legacy hostname, which effectively says, well, yeah, this grotov.gnu guy, on the legacy system, it's called grotov.org. So when you go and validate against the CA system, if you have to, well, if the certificate says grotov.org, that's OK. Right? And if you have to talk to a legacy web server on that machine, just put in a host header that says, I'm going to grotov.org, as opposed to grotov.gnu. Right? So the web server goes and says, I want www.body.gnu. The proxy translates it to, oh, yeah, I'm going to go to body.gnu, but I'm going to put in bobswebsite.com. Right? And yeah. Second possibility, again, was SSL certificate. The local proxy effectively is a certificate authority. We have scripts to automatically import the certificate of this certificate authority that runs on your own machine into your own browser. So you're trusting just on loopback here. Right? You're doing yourself a man in the middle, right? That's safe, if your own machine is safe. So again, the web request goes to bob.gnu. Actually goes out to bobswebsite.com. We validate the answer. Again, we can validate against X509 PKI, or we could validate against the TLSA record, depends on whatever is in the DNS system. And we tell the browser, yeah, this is a valid certificate for bob.gnu. I will trust us because we are his trusted CA. OK. Now, proxies are a mess. Let me just say this. The proxy does not work as well as I would like it to. So in the long term, it would, of course, be nicer to just integrate this understanding into the browser. If we have virtual hosting, we could, of course, just put another header in saying, OK, please don't go for the legacy hostname. Here's the GNS zone. I want this public keys web server instead of a hostname record. And again, if we move to TLSA records as opposed to using X509 existing PKI, we are, again, better off there. OK. Relative names. So we have this notion that in some DNS record types, I can put in names of other names. For example, in the NS record, I can put mail.gnu.org, right? Or in CNAME records, I put whatever the real canonical name of the machine is called something else. Now here, if we put in an absolute name, I can delegate to DNS. I can put in .ziki, or I can put in a relative name. So if you put .plus at the end, it says, the name I'm giving you in this record is relative to what you've resolved it from. All right, so we just use relative host names with .plus, which, again, would be nice if browsers supported those kind of links. New record types, so we saw already, we have public key records, we've got NIC records, and legacy hostname records. We've added records GNS to DNS, so we can say, OK, this subdomain now go back to DNS and resolve using DNS. We have VPN records where we can say, OK, this machine is actually hosted within the peer-to-peer overlay, establish a peer-to-peer tunnel to the target, relay the IP traffic over it, and when a normal legacy application comes and says, I want an IP address, we'll give it one of the virtual interface and synthesize it. We have phone records for conversation. And yeah, that was the very short version of that. Bart will present more about conversation. Florian might present some more on GNU Crypto at the YTPY assembly. And Julian Kirsch will present our approach to port knocking. So please come to our assembly in the next couple of days and have more fun with secure networking. There are also, of course, concerns with how do I integrate this with my application. So we have, as I said, a SOX proxy. You can plug it into NSS, this libc name services switch as a plugin. We can intercept DNS packets using the DNS service, effectively rewrites your firewall rules to give all DNS traffic to us, and then we can mess with it if needed. We have a C API to access the whole thing. We have an inter-process communication protocol if you hate C, and there's a command line tool. Or, of course, you can write your own little C code and call our command line tool. Many ways to integrate it. GNS is part of GNU since 0.93, but we changed all of the crypto in 0.10, which is out like 4 days ago now. International domain names are supported, in case you're wondering. The installation, however, I should warn you, is non-trivial. I wrote instructions for start with Debian stable and start with unpinning and mixing your system with unstable and stable, and then download a couple of source codes. For not all of our record types, we have nice GUIs, but for most of them, we're trying to have a GNS key exchange party where you print your QR codes and give them to your buddies so that they have been introduced. Of course, you can then put into your DNS zones your PGP keys if you want. That's great. So go ahead, install GNU today, create your private keys. You can use GNU BCD, the business card daemon, to launch a web server where you can type in your details and get the PDF with your business card. Need to install LaTeX, though. And you can give the PDFs to Harlan for printing. Thank you.
Thank you. You're a really quick speaker.
I can speed up, and no problem. It's the questions that people follow.
I've seen this. If there are any questions, you can ask them now. I know there's at least one question in the internet, and I think we start with this question.
User Pepper64 wants to know about collision detection on key lookup, especially with short keys.
Traditional attacks on key lookup.
Yeah, collision detection on key lookup.
Collision detection on key lookup.
Yeah.
What kind of collision? We have the public keys. We don't even use hashes of public keys here, so I'm not sure what kind of collisions he's thinking about.
I think in the DHT or something.
OK, the DHT uses 512-bit hashes. We assume that there aren't collisions there. The likelihood of there being a 512-bit collision in the DHT with a decent hash function, it's more likely you get hit by lightning. Way more likely.
OK, then microphone 2.
Bit of a technical question, but I don't quite understand how your set differencing or set resolution thing is that efficient, because you rely on the setup of all these Bloom filters, and the way I understand it, like setting up a Bloom filter is O of n.
Yeah, but you do this once. You don't have to do it for every interaction.
And it's amortized, so each time you receive a revocation, you can pre-compute the Bloom filters. So
okay, I was
That's
it's amortized. You can do it once ahead of time.
Okay.
And most importantly, this is really only local CPU consumption. On the network, you don't have to do this. So what I'm, as a networking person, concerned about is how much network traffic do I have? The fact that I might have a database with 1 million entries, I have to do an iteration over once.
So the circular...
I'm curious to see us having 1 million revocation keys first.
Right. So the circular slide that had like the multiple IBVs inside each other,
yeah.
This is something that continues to exist on your system. This is not something you compute when you meet another peer-to-peer server.
The strata estimator is actually totally static. So
Okay.
for the IBFs, you may have to recompute a larger one if some of the reconciliations fail. But this data structure is totally static for your whole
Thank you.
set.
OK, there's another question.
Yeah, I had a question about, for example, dynamic DNS, what we have today, and if you have changing IP addresses, how fast can you propagate these in the network if you don't know your new IP address in, say, 2
OK,
days?
so the question, let me repeat it, was, suppose I have DIN DNS and my telecom changes my IP address every 24 hours and I can't predict. So the shadow records won't help me at all because I don't know what I have as an IP address tomorrow. Well, that's again a question of how good is the DHT. And yes, you might have a downtime of a couple of minutes to an hour depending on how aggressive you put stuff into the DHT. But really, ultimately, I wouldn't even want to use IP addresses in there. I want to host stuff in the peer-to-peer network. I want to have social applications where I address my friends And I may not have this problem with IPs changing so much. But yes, the DHT is then again the question of how fast do we go things. So that's a performance issue, but it's not a security issue.
Okay, another question at microphone 2.
What is the use case? I mean, I can see a lot of use case for geeks and but in commercial applications and on large scale, do you think there is a concept how one can use it there?
Well, my first use case that I'm trying to get implemented and working nicely is GNU conversation, where the idea is I want to call you. I'm going to put, u.gnu as in call u.gnu, and that's your address. I don't need a, company that I trust with managing names. I don't need a big XMPP trust-based federation. I can just say, okay, I want to call you. You gave me your business card. Now you say, hey, you should call my buddy, and I just use buddy.u.gnu, and I have your buddy securely, right? So for those kind of social networking applications, these are my friends. These are my social rooms where we meet, where we exchange information, bulletin boards. Where these kind of identity management applications that are fundamentally decentralized, where right now we can't even get people to use DNS because they don't want to pay the registration fees and they can't administer DNS. Printing out these business cards when you are able to install the software and giving that to your friend, and then the friend saying, oh yeah, now I have you as friend.gnu, right? And now I can call you. Now I can access your social profile. Now I can do all of these things with that. I think that is something that we can get into the mainstream.
Thank you.
Yes, another question at microphone 1.
Is it? Well, yeah. So the way I understand it, you provide authenticity and integrity, and so that means if I get a message, I know it is from that person and so on. And what about robustness? I mean, what if somebody actually tries to screw up your system, maybe by flooding it with wrong messages, or like, the NSA, let's say, has a botnet and tries to flood everything with wrong messages, and maybe tries to corrupt also hash tables on your side and chooses the message as well. How would you say basically your system would work out?
So the question is, what if somebody attacks your DHT effectively? Yeah. Well, first layer of defense we have is you can't give us invalid records. They have to at least be valid signed. But yes, if you have lots of bandwidth, you can just DDoS us. And yeah, well, most systems don't survive a DDoS unless they are big enough, right? I can't fix that. Overall, we of course try to have a DHT that itself is efficient, so you have a hard time making very expensive operations happen. We try to route around peers that are misbehaving in the DHT. But that's a question of how do we secure the DHT. I didn't talk about the DHT here because I didn't have 5 hours. So I'm sorry, but okay. You can read Nathan Evans' PhD thesis or our paper on R5N, which is the GNU DHT, which has some more details and measurements and experiments on our current DHT. Now notice the GNU Name System, yes, it needs a DHT. The theory works with any DHT, right? So if you have a better one, let us know.
Okay. Okay, we have another question in the internet.
The question is, if revocation lists grow too big, is there a plan for a versioning of lists?
Okay, so the question was, if revocation lists grow too big, is there a plan for versioning of lists? There was a plan where I would, in the far future, implementing a slight extension of the protocol where I say, if I've talked to this peer recently and we reconciled our revocation lists, and we know we had 1,000 entries in that revocation list, I can just skip going over those 1,000 at that point. So if I have interacted with that peer recently before, I only have to go over all of the entries that are newer than that. But I don't quite see that being necessary for quite some time, honestly. I have not really gotten the data, but I don't think even for X509 PKI there are all that many revocations to worry about this. Right? Maybe there should be, but in practice, I personally think revocations are only going to be done by high-profile users that really got badly hit. And most users are probably going to A, forget to create their revocation certificate, and B, not even notice that they got compromised, or C, not care. So this is more really a feature for if you're Jacob Applebaum and you really need to revoke your key, then you have a mechanism and then you'll be hard to stop.
Okay, another question over here.
I don't really understand why you would need to keep the revocation certificates forever. Couldn't you just limit the lifetime of everything that's put into the DHT?
Okay, the question was, can you limit the lifetime of everything in the DHT? In the DHT, yes. But whenever I get something from the DHT, what we didn't talk about here was we have a local cache. And the local cache just looks at how long was this record valid? And I can, of course, say, my delegation to you is valid forever, right? And I can't take that back even. right? So the problem is, and somebody might have taken that into his cache, which is great. He doesn't need to go back to the DHT. He doesn't need to have DHT availability. All of that doesn't matter. He has it all in his local cache. But now it's in the local cache. Even if the DHT doesn't have it anymore, it might still be used, and we have to prevent that. Right, so it's really for the case where somebody picked an excessively long expiration time for p-key delegation.
But couldn't you just require that it needs to be refreshed after, say, 6 months or something?
Well, if I require that something needs to be refreshed, that again opens the possibility for censorship. I could say, okay, I'm going to force people to delete something, right? To remove something. I want to make sure that, yeah, if I met this guy and nothing compromised the security, no, it's going to stay valid forever. I don't need to have another lookup. Don't need to expose to the rest of the world even that I'm doing a lookup, even if they can't tell what I'm doing. Okay.
Okay, and back there, another question.
It seems to me that it's quite complicated to fit this into the current stack with the browser and everything. My question would be, is that how much better can you improve this technique that you just described?
Okay, the question was how much better can I improve the technique I described? I don't know. We don't know a better way, otherwise we would have done it.
Okay, let me rephrase it. Do you think it would be possible to get the cooperation of browser vendors and stuff like that with this?
I think there is a certain browser vendor, which is called the Tor Browser Bundle, and we've been talking with these people a bit, that might be rather interested in adding support for this. I do not think it's likely that we're going to make it into Internet Explorer anytime soon.
Thanks.
Okay, I don't see any other questions. We have 5 minutes left, but you can decide if you want to tell anything else.
No, thank you. Go spend those 5 minutes installing.
Okay, then thank you again. It was very nice to see you.